There is an 835-foot bridge sitting in the historical record that most people have never heard of. It was built in 1852 in Wyoming Territory, spanning the width of 8 modern highway lanes, resting on 23 hand-built stone-filled piers, and the man who designed it was a French fur trapper named Jean-Baptiste Richard, who had no engineering degree, no concrete, no cranes, and no blueprint drawn by anyone with a license to draw one. He just knew wood, he knew water, he knew what holds and what does not. More than 100,000 immigrants crossed that bridge on their way to Oregon, California, and Utah. Fully loaded wagons, livestock, entire families trusted their lives to it. It stood, and every one of them made it. And today, with all our technology, with hardware stores and chemically treated engineered lumber, we have trouble building a backyard deck that does not rot in 5 years. Something was lost. Tonight, we find out exactly what. Picture 1865, the Raton Pass on the border of Colorado and New Mexico territory. A man named Richens Lacey Wooten, known across the entire frontier simply as Uncle Dick, is standing at the foot of a 27-mile stretch of some of the most violent, unforgiving terrain in the American West. He is 49 years old. He has already spent 3 decades as a trapper, buffalo hunter, army scout, and trader. He has crossed deserts alone. He has survived encounters that would make most people's legs go weak just reading about them. And now, on this particular morning, he looks at a creek that has been slowing wagon trains for decades, and he decides, quietly and without ceremony, that he is going to build a bridge over it. Not just one, 26 of them. Across the entire pass, no hardware store, no lumber yard, no structural engineer on retainer, no lag bolts sold in a blister pack, just his hands, a broadaxe, an adze, a froe, an auger, and a draw knife. The kind of tools you have to explain to people today, the kind of tools that used to be in every barn in America. By the time Wooten finished, he had cut a road through solid rock, blasted hillsides, and spanned 26 creek crossings with timber bridges solid enough to carry fully loaded freight wagons weighing 3 tons or more. He charged $1.50 per wagon and was clearing $600 a month. The railroad eventually bought him out in 1878 because the only thing more powerful than his road was the fact that it worked. So what did he know that we've forgotten? What did these men understand about wood and water and weight that somehow, somewhere between then and now, got traded away for something we were told was better? Before we go further, tell me this. Have you ever tried to build something with your hands? A fence post, a deck, a simple footbridge over a ditch on your property, and watched it fall apart in 3 years? If you have, I want you to know this is not your fault, not even close to your fault. Tell me below and tell me what broke. What you're about to discover will change how you see every piece of lumber sold in every big box store in this country. Walk into any home improvement warehouse today and look at the lumber aisle. Pull a 2x10 off the rack. Feel the weight of it. It is light, lighter than it should be. Look at the end grain. Those rings are packed close together, 12 to 20 per inch if you are lucky, but more often you will count 6, maybe 8. The boards grew fast in a plantation where they pumped the soil with nitrogen and irrigated constantly to push growth cycles. That wood is young, green inside even when it looks dry. Stressed. The cells are large and thin-walled because the tree never had to fight for anything. It grew fast and soft, and it will rot just as fast. Now contrast that with what Wooten had access to. Old-growth ponderosa pine from the slopes of the Sangre de Cristo Mountains, black locust from the creek bottoms, trees that had spent 100 years or more fighting drought. freezing, thawing, competing for light. Their rings were compressed so tightly you needed a magnifying glass to count them all. The cells were small and thick-walled, packed with natural resins and tannins, the wood's own armor system that fought moisture and insects without any pressure treatment, without any chemical bath, without a single ingredient you cannot pronounce. That wood did not rot easily. It did not want to. It had spent a century learning how not to. Here is where it gets worse. The modern construction industry figured out decades ago that slow-grown, old-growth timber was running out. So instead of changing how they sourced wood, they changed what they sold you, and then handed you a can of preservative and told you the problem was solved. It was not solved. It was transferred. Transferred to you, your wallet, your weekend, and your increasingly saggy deck. Let's talk about the actual engineering, because these men were engineers. They just did not call themselves that, and nobody gave them a certificate. The foundation of everything they built was a concept called the crib pier. Imagine building a small log cabin, no roof, no floor, just 4 walls rising out of the riverbed. Now fill every inch of that cabin with rock and gravel. Let the river pack it tight and lay your bridge beams across the top of it. That is a crib pier. That is exactly what John Baptiste Richard used at every one of the 23 mid-river supports on Reshaw's bridge. Alternating layers of logs running perpendicular to each other, like the world's most deliberate game of Lincoln logs, interlocked at every corner so that each layer locks the one below it and supports the one above it. The weight of the stone filling does not just sit inside the crib, it activates the friction between every layer of log. The heavier the load, the more the whole structure presses down and inward, tightening the joints. It works harder under stress, not softer. Think of it like a Chinese finger trap made of pine logs and river stone. Modern bridge piers work through brute compressive strength, pour enough concrete thick enough, and it does not move. But concrete cracks under freeze-thaw cycles. It spalls, it corrodes the rebar inside it. USDA Forest Products Laboratory, in a nationwide study of American timber bridges conducted alongside the Federal Highway Administration, confirmed that properly built timber bridges routinely outlast 90 years of active service, and that over 1,000 timber vehicular bridges, at least 90 years old, remain in use across the United States right now, today. 71,200 timber bridges, 12% of every bridge with a span over 20 feet in this country, still standing, still holding trucks. If you are finding this valuable, hit the like button right now, because what is coming next is the part they really do not want you thinking about too hard. Now here is the part that should make you genuinely angry. Not at a person, at a decision. A series of decisions made in boardrooms and engineering schools starting in the 1840s that stripped this knowledge out of the culture as systematically and completely as if someone had gone through every library and pulled the relevant pages. It started with the railroads. Locomotives in the 1840s weighed around 10 tons. By the 1870s, they were pushing 30 tons and climbing. Timber bridges that had served wagons perfectly well for generations simply could not carry that load across long spans without expensive and skilled maintenance. So the railroad industry began lobbying for iron and then steel, and as they did, they funded the engineering schools, the professional licensing boards, and the government bridge standards that would eventually write timber completely out of the acceptable materials list for any publicly funded road crossing. By the 1880s, bridge companies were shipping prefabricated steel trusses by catalog. You picked a span, paid a price, the parts arrived by rail, and you bolted them together. No broadaxe skill required, no knowledge of wood grain or natural rot resistance or crib joinery. The craft became a commodity, and the men who held the knowledge, men like Uncle Dick Wooten, like the builders of Reshaw's Bridge, retired or died, and nobody was writing down what they knew, because everyone assumed the engineers had something better. They did not. They had something faster, something cheaper to produce at industrial scale, something that made the bridge building industry an industry rather than a craft. That is not the same thing as better. And the viewer who paid for a pressure-treated deck that went spongy in 3 years already knows that, even if they did not have the language for it until just now. You are not bad at building things. You were sold bad materials and given no knowledge of what made the old ones work. Let's get into the specific techniques, layer by layer, because this is the knowledge that disappeared, and it is not complicated once someone actually explains it. The first thing frontier builders understood was wood selection. Not all trees are equal, and not all parts of a tree are equal. The heartwood, the dark inner core, is the part that resists rot. It is denser, richer in natural preservative compounds, and structurally stiffer than the pale sapwood surrounding it. When Wooten's crew selected a log for a bridge stringer, they were choosing trees where the heartwood ran wide and the sapwood was thin. They were choosing black locust when they could find it, a wood so resistant to rot that fence posts made from it were documented to last 50 years in ground contact without any treatment. They were choosing eastern red cedar, Osage orange, bur oak, species that had co-evolved with the wet soils and seasonal floods they were being asked to span. They were choosing the tree for the job, not accepting whatever came off a pallet. The second thing they understood was placement. Log stringers, the main beams running the length of the bridge, were always laid with the natural crown of the log facing upward. Every log has a slight bow to it from growing toward light. Under load, a log wants to deflect, to sag. A crown-up placement means the load is fighting the natural curve of the wood before it starts fighting the wood's structural limits. The bridge deflects less. It lasts longer. This is not folklore. This is basic material science that modern engineers rediscovered in studies of traditional construction, then quietly published in forestry journals that nobody reads. The third technique, and this one will stop you cold when you understand what it means, is the tree nail. A tree nail is a wooden peg, and it is the reason these bridges stayed together. Split from straight-grained oak or locust using a wedge-shaped blade called a froe, shaped smooth on a shaving horse with a draw knife, then driven into a hole bored slightly undersized with a hand auger. When the peg goes into that hole, the friction is immediate and immense. But here is the genius part. When that peg gets wet, as every bridge peg does, it swells. It swells against the walls of the hole. The joint does not loosen in rain. The joint tightens. Every time water touches it, the connection gets stronger. Compare that to a modern galvanized nail, which expands and contracts on a different thermal cycle than the wood around it, creating tiny gaps, capturing moisture, then rusting. And as it rusts, it stains. It corrodes the surrounding wood cells. And the whole connection begins its slow collapse from the inside out. Nobody sells you a nail and tells you that story. But the story is true. The fourth element is the covered roof. Uncovered log bridges lasted 10 to 20 years in documented historical records, closer to 15 on average in the wet mountain climates of the West. Covered bridges, where a simple gable roof sheltered the structural timbers from direct rain and sun, routinely lasted a century or more. Around 14,000 covered bridges were built in the United States. Roughly 750 to 900 of them survive today, many from the building era from 1825 to 1875. That is not sentiment. That is a roof doing in wood what a garage does for a car. The oldest covered bridge in the country, in Ashtabula County, Ohio, dates to 1867. It is still open to traffic. So why did we stop? We already touched on the railroads, but the full picture has 3 causes, and they hit in sequence like a slow avalanche. Speed first. A timber bridge built by craftsmen who knew what they were doing required weeks of work. selecting timber, hewing, cutting joints, assembling cribs, and boring tree nail holes by hand. A prefabricated steel truss, shipped in sections and bolted together, could go up in days. At the scale of a railroad needing thousands of bridges across a continent in 20 years, days beat weeks every single time. There was no contest. Cost second, old-growth timber, the only kind worth building with, was running out by the late 1800s as forests were cleared for agriculture and the first wave of industrial logging. The cost of quality timber climbed just as mass-produced steel was falling. The economics flipped inside a generation. Steel third, the Bessemer steel process, perfected in the 1860s, allowed mass production of structural steel at a price that made iron obsolete and wood seem ancient. When the professional engineering associations codified bridge standards in the late 1800s, they wrote those standards around steel. Timber was grandfathered into rural use, but was effectively frozen out of public infrastructure. The engineers who trained in those standards trained the next generation, and within 2 generations, the practical knowledge of how to select, season, joint, and maintain a timber bridge had essentially vanished from the professional class entirely. The hidden cost you are now paying is that steel and concrete bridges require continuous maintenance budgets, are vulnerable to corrosion, suffer from freeze-thaw spalling, and carry a roughly 75 to 100-year design life. The USDA Forest Products Laboratory pointedly notes that this is not based on actual performance data for either material. The timber bridges we do have are lasting longer than the models predicted because the trees they were built from were better than anything grown fast in a modern plantation. So what do you actually do with this? 3 options, in order from easiest to most involved. Option 1. The next time you are buying lumber for any outdoor project, like a footbridge over a drainage ditch, a garden bed frame, or a simple crossing on your property, ask specifically for black locust, Osage orange, or eastern red cedar heartwood. Do not pick pressure-treated pine, which is young sapwood soaked in copper azole compounds that require a respirator during cutting and special disposal of sawdust. Choose real auroch-resistant heartwood. Specialty lumber yards carry it. Sawmills that do custom cutting can source it. It costs more per board foot. It lasts 4 to 6 times longer. The math is not close. Option 2. If you want to build an actual footbridge using these methods, here is the sequence. First, find 2 logs of roughly 12-inch diameter and at least 2 feet longer than your span. Green-black locust or white oak are ideal. Hew them flat on top using a broadaxe, making a clean bearing surface for your deck. Set them on stone or treated wood mud sills. Set firmly into each bank. Crown side up. Space them roughly 2.5 feet apart. Lay deck planks or split puncheons perpendicular across both stringers, and spike them down. Or if you want to build it the real way, bore through deck and stringer with an auger, and drive dry locust pegs that will swell tight in the first rain. A simple gable shed roof over the structure, even just a corrugated metal roof on 4 posts, will double the bridge's life by keeping direct weather off the joinery. A bridge built this way on a farm crossing or a private trail will outlast you. Option 3. If you are not ready to build anything, start by identifying the wood you already have. Pull back the fascia board on any outdoor structure you own. Look at the end grain. Count the rings per inch. If you can count them easily, 8, 10, 12 per inch, that is slow-grown, dense wood, and it will serve you well. If the rings are wide and few, that is plantation wood, and it will not. That one test, which costs you nothing, tells you everything about why some things last and some things do not. Uncle Dick Wooten was not a primitive man stumbling through the wilderness. He was a precision engineer operating without the institutional validation we require today, and he built 26 bridges in mountain terrain that moved enough traffic to outperform a railroad's projections until they had to buy him out. John Baptiste Richard built a structure 835 feet long over a wild Wyoming river with hand tools and a knowledge of wood that no university was teaching, that no textbook had encoded, that lived entirely in the hands and eyes of men who learned it by doing it. Those bridges worked. The immigrants got through. The knowledge was real. The secret was never lost. It was traded away, traded for speed, for scale, for the industrial convenience of a standardized system that needed you not to know how to build without it. We're done accepting that trade. This channel is digging up the things the modern world buried, the skills, the methods, the materials that worked before anyone could make money selling you a replacement. Tell us in the comments, what do you want us to investigate next? What did your grandfather build that you never understood how he did it? We want to know. And subscribe, because we are just getting started.